Welcome to Tomorrow Unveiled. If you ever need a week's worth of global space news, and I mean everything from geopolitics to deep science distilled into pure, actionable insight, you have absolutely come to the right place.
And what a week it's been. Our research team has compiled a stack of sources that really describe a period of extreme, almost jarring contrasts in the space industry.
Jarring is the right word, a week of just total divergence.
Exactly. We saw these historic dollar investments, particularly from the U.S. defense sector, just flowing into space infrastructure at a rate we've never seen before.
Setting records for industrial production, for cadence.
Yeah, and at the exact same time, we saw some incredibly high-profile, really strategic technical failures in rocketry across the globe.
Yeah.
It's just a brutal reminder of how hard this still is.
It is. So our mission today on Tomorrow Unveiled is to synthesize the most important nuggets of knowledge from this really complex period, which is spanning December 17th through the 24th, 2025. We're going to dig into the irreversible massive shift to military space. Then there's this shocking new scientific hypothesis that basically rewrites what we thought we knew about Saturn's moon Titan.
It's a huge one.
And finally, the harsh reality that competing nations are facing as they struggle to catch up in the reusability race.
The information collected by our dedicated research team, it suggests this week wasn't just busy, it was a crystallization, that's the word they use,
Crystallization of what?
of several long-term, tectonic trends,
Mm-hmm.
the decisions made, the events that unfolded this week, these massive SDA contracts, the relentless launch tempo, the critical failures in Asia. They're all actively shaping the space economy.
Not just the economy, right?
No, the geopolitical balance of power.
Right.
And even, as you said, the future of astrobiology for the next decade. Our goal here is to just synthesize the most important details and what they mean to make the future of space a little clearer for you.
Okay, so let's start with the money, because the flow of capital is really what's driving the fastest changes and the most profound strategic shifts right now. And the biggest headline, I mean, hands down, was that colossal contract from the U.S. Space Development Agency, the SDA.
The $3.5 billion contract.
$3.5 billion.
And that figure, it isn't just large, it's absolutely transformative. This award was for what's called Tranche 3 of the tracking layer.
Okay, so what does that mean in practice?
It means the design and production of 72 new missile warning and tracking satellites that will operate in low Earth orbit. But it's more than that. It doesn't just fund the satellites. It solidifies the doctrinal reality of what the SDA calls the proliferated warfighter space architecture.
The PWSA. Okay, let's unpack that, because this PWSA shift, it represents a total doctrinal overhaul, something our listeners really need to get their heads around. For decades, the U.S. military space paradigm was, well, it was centralized, expensive, and kind of fragile. They called it exquisite.
Exquisite.
So what did that mean, exquisite, in this context? And why is this $3.5 billion basically sealing its replacement?
Exquisite meant building a few highly specialized, enormous satellites. I mean, think about structures the size of a school bus,
Wow.
costing billions of dollars each. And they place them in these extremely high, very predictable orbits, usually geosynchronous orbit or GEO.
So everyone knew where they were.
Exactly. They were centralized, they were irreplaceable, and because of that, they were extremely tempting high-value targets. One hit could cripple the whole system.
Okay.
The PWSA, which is now getting this full funding, is the conceptual and physical opposite. It is a philosophy built on resilience.
Resilience through...
Resilience to redundancy, yeah. We are talking about hundreds, eventually thousands, of smaller, cheaper, mass-produced satellites. They're continuously refreshed, spread out all over low Earth orbit. So if you attack the network, you merely take out a single node.
Not the whole system.
Not the entire system. Think of it like this. The old model was a centralized bank vault with all the wealth in one single place.
Okay.
The new model is more like a distributed ledger system, a blockchain, where the data is spread across so many points, it's basically impossible to crash the entire system.
That's a great analogy. It really clarifies the resilience concept. So why is Tranche 3, specifically, the true pivot point here? I know Tranche 0 was a demo, Tranche 1 gave some warning capability. What new capability is this $3.5 billion buying?
Tranche 3 is the pivot from just warning to enabling active defense.
Active defense.
The explicit focus of these 72 new satellites is tracking and maintaining custody of advanced threats,
What kind of threats are we talking about?
primarily hypersonic glide vehicles,
Mm.
or HGVs. These weapons are a unique challenge.
Because they fly low and they're fast.
Right, they fly lower than traditional ballistic missiles, which
Mhm.
makes them invisible to those old legacy GEO systems.
Mhm.
But they also maneuver so fast that it's difficult for ground-based radar to maintain a lock on them.
So you get a blip, and then it's gone.
Precisely.
Hmm.
This new LEO layer will create a persistent global mesh network that can maintain what the sources called continuous custody of an HDV
Continuous custody.
throughout its entire flight path, from launch to target.
I saw some specific language in the contract documents cited by our research team. It mentioned fire control quality. Can you explain why that specific phrase changes the strategic landscape so dramatically?
That is the strategic differentiator.
Hmm.
And this is where understanding the militarization of EO becomes so critical. Fire control quality means that the satellite network is generating data that is precise enough in terms of position, velocity, predicted trajectory,
To do what?
to actually guide an interceptor missile to the target.
Wow. So it's not just, hey, something is coming.
No, it's not general awareness. It's targeting data. It enables the completion of the kill chain from space. It turns AEA into a key component of missile defense systems globally.
Okay, hold on. Isn't there a huge risk of escalation here?
How so?
Well, if the U.S. is placing fire control quality sensors in orbit sensors designed to help destroy an adversary's best weapons, doesn't that make the entire constellation a prime target?
It does.
Isn't that inherently destabilizing politically?
That is the core geopolitical question that the sources really grappled with. By moving to fire control, the SDA is essentially accepting that Leie is no longer a sanctuary.
It's a battlefield.
It's a contested warfighting domain. And the entire PWSA architecture is designed around this inherent risk.
Okay, so how do they manage that risk?
The idea is, if the sensors are cheap, proliferated, and rapidly replaceable, the cost for an adversary to degrade the system is far, far higher than the cost for the U.S. to maintain it. This huge investment is an attempt to create an economic and industrial mismatch.
Making it too expensive to fight.
Exactly. The proliferation strategy is both a defensive and a deterrent mechanism. The sheer volume of satellites is meant to make counter-proliferation, trying to destroy them all, economically and technologically impractical.
So it's a strategy of attrition, almost.
In a way, yes.
Now, here's where it gets really interesting on the industrial side. Who actually got these massive contracts?
The contracts were split among 4 prime contractors. You have your legacy defense giants, Lockheed Martin, L3 Harris, and Northrop Grumman.
The usual suspects.
But the surprising inclusion, the one that validates an entire business model, was Rocket Lab.
Rocket Lab, the small launch company.
The very same. They secured an $805 million slice of that pie.
Wow.
For 18 of the MWTD, or missile warning, tracking, and defense variants.
So Rocket Lab, the company that started with the small electron rocket and, a very charismatic CEO, is now a prime defense systems contractor. They're standing alongside the absolute titans of the military-industrial complex. How did they pull that off?
It is the absolute validation of their aggressive vertical integration strategy.
Meaning they do everything in-house.
Everything. Rocket Lab has been diligently acquiring and building out capabilities to move up the value chain. They aren't just selling launch services anymore.
Right.
They're selling the entire end-to-end space system. They provide the satellite bus, the physical structure, the components, the solar panels, the flight software, the mission ops, all of it.
So this single defense award just completely changes their standing in the industry.
Dramatically. It provides crucial revenue stability against the volatility of the commercial launch market. And according to analysis from financial firms, it essentially doubles their space systems backlog.
It transforms them.
It transforms them from a niche launch provider into a major industrial prime.
And speaking of that launch market volatility, you said Rocket Lab is succeeding by diversifying away from the brutal price wars. And those wars are really being waged by one company. We have to talk about the unrelenting operational dominance of that company, SpaceX. The research team confirmed that they achieved their 160th Falcon 9 launch of 2025 this week.
That number, it's not just large. It is statistically distorting the entire global launch market
Distorting how?
in ways that, traditional economic models just struggle to cope with. Our sources indicate that in 2025, SpaceX has lofted more total mass to orbit than all other nations and companies combined.
Combined. That's staggering.
It is. And this relentless industrial scale tempo creates economies of scale that no competitor can possibly match on price.
It's a numbers game. If you're launching 5 times a year, you're amortizing your fixed costs, your factory, your people, your R&D over just 5 missions.
Right.
But if you're launching 160 times, the fixed cost per flight just plummets into a territory that it changes everything for every single satellite operator.
Precisely. That pricing structure sets an artificial price floor for the entire market. It means competitors have to choose between losing money on every launch they sell.
Or losing all their customers.
Exactly. The operational cadence is a competitive weapon. And that number, 160, also reflects an unprecedented maturity in their supply chain, their launch readiness procedures.
They can just move faster than anyone else.
They can recycle hardware and workforce faster than anyone else can even produce expendable hardware. It's forcing everyone else, legacy companies, ambitious state programs, to just scramble to remain relevant.
Which brings us to a major piece of leadership turbulence this week that just underscores that intense pressure. The unexpected resignation of Tory Bruno, the president and CEO of United Launch Alliance, ULA.
This is a big deal. His departure adds a severe layer of managerial and operational uncertainty at a critically sensitive time for ULA.
Why so critical right now?
Bruno was the one guiding the company through a necessary but very stressful transition. He oversaw the retirement of their workhorse, the Delta Phi Heavy, and he led the development of the new Vulcan rocket.
Which is ULA's big answer to the SpaceX threat.
It's their crucial response, yes, but Vulcan has faced significant challenges.
Right, the delays with the Blue Origin engines, the BC-4s.
So how does this leadership shift affect ULA's standing, especially with your main customer, the U.S. government?
The uncertainty is amplified because ULA is a critical provider of what's called National Security Space Launch, or NSSL.
The government relies on having two providers,
Right.
a dual-source strategy.
Exactly, to ensure launch access. So any instability at ULA puts pressure back on the Pentagon. They need to ensure Vulcan reaches full operational capability and fast.
And losing a key leader like Bruno right now just complicates everything. The stabilization of Vulcan's prediction, its market footing, it all gets harder.
It really signals that the pressure cooker that is the commercial launch market is reaching a boiling point for some of these legacy players.
They just can't keep pace with the sheer speed of their primary competitor.
Okay, we just threw a huge amount of information at you. From $3.5 billion defense contracts to Rocket Lab's pivot and ULA's leadership shift. This is complex, fast-moving stuff, and we really appreciate you staying with us for this deep look into Tomorrow Unveiled. So if you're finding this insightful, maybe this is a good moment to just say, if you're on YouTube, please take a second to like this video and subscribe to Tomorrow Unveiled. And, consider hitting that new hype button. It really helped us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. All right, let's shift gears a bit. Let's move from the economics and geopolitics of space to the fundamental engineering that makes deep space exploration even possible. This week saw some major breakthroughs in enabling technologies. Let's start with the propulsion systems for the Lunar Gateway.
All right. L3 Harris delivered 3 12-kilowatt Advanced Electric Propulsion Systems, or AEPS, thrusters to NASA. And this is a huge, tangible milestone for the Artemis program's critical lunar infrastructure.
We hear about Hall effect thrusters all the time, especially with big constellations like Starlink. But what makes these 12-kilowatt units so different from the, 1 or 2 kilowatt thrusters we see on a standard LEO satellite?
It's a critical leap in power density and in mission capability. The low-power thrusters on LEO satellites are really just for minor course corrections, or maybe for deorbiting at the end of their life.
Small adjustments.
Tiny adjustments. The AEPS units, by contrast, are designed for the demanding, continuous job of maintaining the Lunar Gateway's very complicated orbit.
That's the near rectilinear halo orbit, the NRHO.
Correct.
The NRHO is often called an inherently unstable orbit. For our listeners, what does that actually mean, and why does it make these big 12-kilowatt thrusters so mission critical?
Think of it less like a stable planetary orbit and more like trying to balance a marble on a saddle.
Okay, that's a good visual.
The NRHO is a kind of figure-8 loop around the moon that uses the complex gravity of both the Earth and the moon. It's great because it allows the gateway to stay in continuous contact with Earth, but it's unstable. So without constant, powerful thrust corrections, the station will just drift off course very quickly.
And that's where these thrusters come in.
Exactly. These 12-kilowatt thrusters provide extremely high specific impulse.
Which means they're very fuel efficient.
Incredibly fuel efficient. But they can still deliver the sustained force needed to maintain that complex, demanding orbit for years. And since mass is the ultimate premium in deep space, That fuel efficiency is absolutely vital for mission longevity.
That makes perfect sense. Less fuel mass means more payload mass for crew or for science.
Right.
But propulsion innovation wasn't just limited to these massive power systems. We also saw some novel concepts being tested for much, much smaller spacecraft.
Absolutely. The research team looked at the DUP-LX CubeSat mission. It's testing two novel micropropulsion systems, a fiber-fed pulsed plasma thruster and a monofilament vaporization thruster.
That's a mouthful.
It is, but this is technology designed to give those small satellites, the CubeSats, the agility they desperately need.
And the key innovation here is all about replacing the traditional liquid propellant systems.
Yes, the focus is on using a solid polymer feed material, something like Teflon or Delrin. This is a crucial safety and operational advance.
Why is that so important for these little satellites?
While traditional micropropulsion often relies on pressurized, potentially hazardous liquid propellants like hydrazine.
Nasty stuff.
Very. And it complicates everything. The assembly, the handling, the safety protocols, especially for these smaller, often student-built or specialized commercial CubeSats. By switching to a non-volatile solid polymer that you just vaporize on demand, you get rid of those hazardous liquids entirely.
So it simplifies the whole design.
Dramatically.
Yeah.
And it lowers the barrier to entry for more complex missions using these small spacecraft, giving them real maneuvering capabilities like collision avoidance.
That feels like a really practical, immediate step forward for the industry. But then there's the other end of the spectrum, the concepts that are pushing the very fringe of physics. The reports highlighted a resurgence of highly scrutinized research into propellantless drive.
Yes, reports surfaced again. Researchers presenting findings on systems that claim to generate thrust solely through internal electric fields without expelling any propellant mass at all.
So a reactionless drive?
If the claims were verified, yes. These systems, they often follow in the footsteps of the controversial M drive.
That sounds like science fiction. I mean, if the laws of physics, specifically conservation of momentum, are true, this shouldn't be possible. So why does the research keep happening?
It persists because the need is so critical. The industry is desperate to bypass what's called the tyranny of the rocket equation.
Right. The more you want to speed up, the more fuel you need, which means you need a bigger rocket to lift the fuel, and so on.
It's an exponential problem. A reactionless drive would solve all of deep space travel's challenges in one stroke. But, and this is a big but,
This is where we have to apply some critical thinking.
aggressively.
Yeah.
Our sources note that these concepts have historically failed to withstand rigorous, independent, peer-reviewed verification. The reported thrust almost always turns out to be experimental error.
Like what kind of error?
Thermal drift, magnetic interactions with the test setup, or just simple sensor noise, things that look like thrust but aren't.
So we need to acknowledge the pursuit because it highlights the fundamental frustration with current physics, but we have to remain highly skeptical.
Extremely skeptical until verifiable, repeatable data emerges. The scientific community remains, let's say, unconvinced.
Right.
The persistence of the research just shows the desperation for a breakthrough. But until it's independently confirmed, we have to treat it as an interesting experiment, not a viable propulsion system.
Okay, so moving from propulsion to operations. The challenge of on-orbit servicing, assembly, and manufacturing OSAM, it requires incredible dexterity, especially when you're dealing with non-cooperative objects like tumbling space debris. And the European Space Agency, ESA, successfully tested a fascinating solution this week, a gecko-inspired robotic gripper.
This is a perfect example of biomimicry solving a critical engineering problem in microgravity.
So it literally works like a gecko's foot.
It does. The gripper uses dry adhesive technology engineered to mimic the microscopic hair-like structures, or setae, on a gecko's foot. When you press it against a smooth surface, these microstructures maximize the contact area at a molecular level, and that creates a powerful grip using van der Waals forces.
Van der Waals forces, that's the weak molecular attraction that happens between all materials, right?
Exactly. It's weak at a macro scale, but when you have millions of these tiny contact points, it becomes incredibly strong.
We've seen other ideas for grabbing satellites, like robotic arms or nets or even magnets. What's the key advantage of this gecko adhesion?
The crucial capability is zero-force detachment.
Okay, what does that mean?
It solves a massive problem when you're trying to deorbit debris. If you use a mechanical claw or a harpoon to grab a tumbling target, the act of releasing it usually gives it a big push.
Right, you send it spinning off in another direction.
Unpredictably, yeah. The gecko gripper avoids this. The adhesion, which is strong when you pull on it, can be switched off almost instantly just by changing the direction of the load. You sort of peel it or roll it away.
So you can let go without pushing.
Exactly. It allows the gripper to capture a fragile or tumbling target and then release it without imparting any damaging momentum. It makes debris removal far safer and more practical.
That is a huge step forward for just keeping space clean.
It is.
And in the materials sector, we saw AI accelerating some fundamental breakthroughs. Fujitsu and Tohoku University announced they use their Kozuchi AI platform to speed up the discovery of new high-temperature superconductors.
This is materials informatics delivering massive efficiency gains. Superconductors are materials that conduct electricity with zero resistance, but usually only when they're cooled too, like absolute zero.
Which is impractical for space.
Extremely. High-temperature superconductors are the holy grail for aerospace because they promise to radically reduce the mass and the cooling requirements of electrical systems, making them viable outside of giant labs on the ground.
So what's the direct application of a breakthrough here for future missions, say, to Mars or the Moon?
Two things immediately jump out as game changers. First, superconductors are vital for creating lightweight, active magnetic shields.
To protect against radiation.
To protect the crew, yes. These shields generate powerful fields that can deflect damaging deep space radiation, like galactic cosmic rays. It's essential for long journeys. And second, they're crucial for high-power electric propulsion. Things like advanced magnetoplasma dynamic thrusters or VASIM engines, which require immense magnetic fields that you can only generate efficiently with superconducting coils.
And the AI just makes finding these new materials faster.
Much faster. It uses deep learning to identify subtle relationships in the electron states, turning what used to be a decade-long manual testing process into something much more predictive.
We've talked about billion-dollar contracts in advanced physics, but one mission this week showed that space is also becoming more inclusive. Blue Origin's NS-37 mission carried 6 passengers, and among them was the first wheelchair user to cross the Kármán line.
Yeah, that event, which saw the German aerospace engineer Michaela Benthaus reach space, is a major marker for the maturation of commercial spaceflight.
How so?
Historically, access has been restricted by these incredibly restrictive physical requirements rooted in military pilot standards. This is a tangible step toward dismantling those physical barriers.
It validates the whole commercial model's drive for broader inclusivity.
It does.
What specific engineering and operational details did our research team flag as being necessary to make that possible in a suborbital capsule?
Well, it required a complete reevaluation of accessibility standards in a very technical, fast-paced environment. Blue Origin implemented specialized hardware.
Like what?
Things like a patient transfer board and a customized system to help with getting in and out of the capsule safely, both on the launch tower and inside the vehicle itself. They also had to make sure the launch tower elevators and even the desert landing site were fully compatible with accommodating a wheelchair immediately upon touchdown.
When the G-forces are high.
Exactly. It shows that commercial players aren't just aiming for speed and price. They're actively investing in engineering solutions to broaden the passenger pool.
And that, in turn, broadens the entire market.
For sure.
It's a powerful counter-narrative to the hard-nosed competition we started with, but we have to return to that competitive reality now. Because even as the door opens to more people, the technology itself keeps reminding us just how brutal the learning curve still is. And that reality brings us directly to Asia's struggles this week.
The week was defined by this immense divergence in operational maturity between the U.S. and its major competitors. While SpaceX is hitting launch number 160 and perfecting its booster landings, two of the most ambitious launch programs in Asia suffer these really high-profile setbacks in their quest for reusability.
Proving that the capability gap is still vast. Let's start with China's Long March 12A failure.
The Long March 12A, or CZ-12A, is China's new Methalox rocket. It's explicitly designed as a heavy-lift competitor to the Falcon 9. Its maiden flight was, you could say, a partial success. The upper stage did place the payload into orbit, but the critical primary objective, the first stage recovery attempt, ended in failure. The booster crashed near the designated landing pad and was completely destroyed.
And this wasn't an isolated incident, was it?
Not at all. It followed another vertical landing failure earlier in the month by a private Chinese firm, Landspace, with their Zhuge 3 rocket.
So what is the core problem here? The powerful Methalox engines seem to be working. What's failing in the recovery process?
The consensus compiled by our research team points definitively to a severe guidance, navigation, and control, or GNC, gap.
The GNC gap.
China has demonstrated they have the powerful engines necessary. They have the brute force to lift the rocket and perform the re-entry burns. The overwhelming difficulty lies entirely in the software.
And the sensors? The control logic.
Exactly. The real-time control logic required for a precise, vertical, propulsive landing.
Can you elaborate on why GNC is so much harder than engine power?
Think of the difference between driving a powerful car and performing complex brain surgery. Getting the engine to fire is the easy part.
Right.
The GNC system has to take a skyscraper-sized cylinder falling backward through the atmosphere at Mach speed, a structure that is inherently aerodynamically unstable.
And landed on a dime.
In real time, it has to compute the exact thrust vector, control the grid fins, compensate for wind shear, manage fuel slosh, and guide it with millimeter precision to a tiny landing pad. The software has to predict the future faster than physics can alter it.
And that takes experience.
It requires thousands of successful iterations and refinements, the kind that SpaceX has perfected over a decade of trial and a lot of error.
So it's not a question of manufacturing or metallurgy. It's a question of software sophistication and sheer operational experience.
That's the wedge. Until China can reliably land and reuse its boosters, the U.S. retains this asymmetric economic advantage. Every failed landing forces their programs to rely on less efficient, expendable rockets or tolerate much higher costs.
The mastery of GNC is the real moat protecting the U.S. launch industry's dominance.
It is.
Okay, so if the Chinese failure was a setback in reusability, Japan's new flagship rocket, the H-3, suffered an outright catastrophe.
A catastrophe, yes. A second catastrophic failure in a very short time. And this is particularly worrying given the H-3's strategic role.
This was supposed to be their new, reliable workhorse.
It was. This was a devastating blow for JXA, Japan's space agency. The H-3 was designed to be their new, reliable, cost-effective rocket that would underpin their national security and international cooperation. The failure happened relatively early in the flight. The first stage separated successfully, but then the LE-5B3 upper stage engine.
The one that uses liquid hydrogen and oxygen.
That's the one. It failed completely to ignite for its scheduled burn, and that resulted in the total loss of the mission.
And the payload that was lost, the QZS-5, that was strategically critical, wasn't it?
Absolutely. Losing QZS-5 is strategically painful. This satellite was part of the Quasi-Zenith Satellite System, or QZSS.
Japan's regional GPS?
Exactly. It's a high-precision augmentation to the U.S. GPS network. It provides vital signal reliability, especially in dense urban canyons like Tokyo, where line of sight to traditional GPS satellites is difficult.
So a degradation in that system has real-world effects.
It means diminished service reliability for precision agriculture, for security operations, and for the future rollout of autonomous vehicle tech.
The H-3 now has a 25% failure rate. What does that do to the rocket's future and to Japan's standing in international cooperation?
It creates an immediate existential crisis for the program. The H-3 was designed to be price competitive, aiming to have the launch costs of its predecessor.
But reliability is everything.
Reliability trumps price in the launch market. If the vehicle isn't reliable, no commercial customer will book it. The Japanese government will be forced to use foreign providers for its most sensitive payloads. And beyond that, the H-3 is a key commitment for Japan's international obligations.
Like the Artemis program.
Notably, the LUPEX lunar polar exploration mission with India. This failure rate places Japan's credibility and its participation in major programs like Artemis under serious immediate scrutiny. They have to fix this, and fast.
Moving from these launch failures to the inherent growing risks of just being in low Earth orbit, we saw a stark reminder of the orbital debris crisis this week. A Starlink satellite suffered a catastrophic anomaly.
Our research team confirmed that Starlink satellite 35956, operating at about 418 kilometers up, suffered an internal rupture of its propulsion tank. The sources indicate this was a high-energy event. The satellite immediately started to tumble and entered a period of instability.
And the immediate risk isn't just to the one satellite, it's the cloud of debris it creates.
Exactly. Independent radar tracking immediately detected tens of new debris objects generated by this event. And with well over 9,300 active Starlink satellites in orbit now, any fragmentation event significantly increases the risk of fratricide.
Where debris from one Starlink hits another.
Creating a cascading failure, yeah. This event just intensifies the growing demand for stricter space traffic management regulations globally. The more you put up there, the more inevitable these internal failures become.
And that raises the risk for every single person and satellite in LEO.
Military or commercial, yes.
And speaking of risk, The most dramatic and sobering operational detail of the week was a previously undisclosed incident aboard the Chinese Tiangong space station. It speaks to the direct, immediate threat that debris poses to human life. The sources describe an unprecedented Shenzhou rescue mission.
This is a truly chilling narrative. It just underscores the dangers of LEO.
Yeah.
The Shenzhou 20 return capsule, which was docked to the station, serving as the crew's lifeboat.
Their ride home in an emergency.
Right. It suffered a micrometeoroid strike.
Right.
And while the station itself was fine, the strike critically damaged a viewport window on the capsule.
Rendering it unsafe for re-entry.
Unsafe for the crew's return to Earth, yes.
So in an instant, the crew lost their safe way home. They were stranded in orbit without an emergency return vehicle. How did they resolve that?
China demonstrated truly impressive, I'd say industry-leading, operational agility. They executed a rapid lifeboat protocol.
What did that entail?
The crew of Shenzhou 20 returned home on the newly arrived Shenzhou 21 spacecraft, which meant the Shenzhou 21 crew had to give up their ride.
But that left the station without a lifeboat again.
For a short time, yes. But the real feat was the immediate follow-up. To restore that emergency return capability, China executed an almost immediate high-priority launch of an uncrewed Shenzhou 22.
A dedicated emergency rescue ship.
Exactly.
That requires an unprecedented level of speed of maintaining a hot backup launch readiness that, very few other space powers currently possess.
It does, and the implications are huge. This is the first time a major space power has had to execute a dedicated uncrewed rescue launch for a crew in orbit because of debris damage.
It validates their whole strategy of high readiness.
And it simultaneously underscores that orbital debris is no longer some abstract problem. It is an immediate, severe threat to the lives of every human currently living in LEO. The risk assessment for long-duration stays has to be updated across the board.
Wow. That puts the entire week's events into a very real and human perspective. The stakes have never been higher. If you're listening on a podcast service like Apple Podcasts or Spotify, we would be incredibly grateful if you could just take a moment right now to leave us a rating and a review for Tomorrow Unveiled. It truly helps us reach new listeners. Okay, let's pull away from the chaos and risk of LEO for a bit and look further out, specifically to the outer solar system and Saturn's largest moon, Titan. Our research team confirmed a groundbreaking study published in the journal Nature this week that challenges one of the most widely held beliefs of modern astrobiology. It's forcing a real planetary science pivot.
For nearly 2 decades, the search for life in the outer solar system has been highly focused on this one hypothesis, that Titan harbors a massive, global subsurface ocean of liquid water.
An ocean nestled beneath its thick, icy crust.
Right. And this belief was based primarily on high-precision gravity and tidal measurements taken years ago by the legendary Cassini mission.
And this new study, when they re-examined that foundational data, what did they find?
They focused on a metric called the Moon's love number.
The love number.
Which, simply put, is just a measure of how much a planetary body deforms under the tidal stress from its parent planet, in this case Saturn. The previously high love number was interpreted as proof of a fluid global ocean that was decoupling the crust from the core.
Okay.
However, the new analysis demonstrated that the observed patterns are also mathematically and physically consistent with a slushy matrix.
A slushy matrix. That sounds far less romantic than a global ocean.
Right.
What does this slush hypothesis actually look like inside Titan?
Instead of a vast continuous ocean, the hypothesis suggests a thick, viscous mixture of ice and rock that hasn't fully separated into distinct layers.
So not a lake, more like...
Well, think of it less like the Great Lakes under the ice and more like a heavily brine-infused heterogeneous layer, a sort of dense, heavy slurry. It might have localized small pockets of meltwater, but definitely not a continuous planetary-scale liquid shell.
This sounds like a fundamental change in how we see Titan's interior. What are the astrobiological implications of replacing a global ocean with localized slush?
The implications are massive and generally less optimistic for the potential of a widespread biosphere.
Why is that?
A global ocean allows for efficient heat and energy transport from a rocky core, where you might have hydrothermal vents, up to the ice shell. It spreads nutrients and heat globally. A slushy matrix, being so viscous, would severely inhibit that large-scale transport of energy and chemicals.
So it forces a change in the search strategy. We have to move from follow the water to follow the energy gradients within the ice.
Precisely. The research team emphasizes that life isn't entirely precluded, but the search has to pivot drastically toward what they're calling cryoaquifers.
Cryoaquifers.
Localized, small, concentrated brine pockets that are maintained by highly energetic internal processes, like focused tidal friction or cryovolcanic activity.
And this discovery, coming out now, is critical for the upcoming Dragonfly mission.
Absolutely critical. It fundamentally impacts the landing site selection and the type of instruments needed for NASA's Dragonfly mission. Have to update their mission parameters based on this new data before the spacecraft even leaves the ground.
Let's pivot back inward now, from the deep past of planetary formation to the near future of industrial space infrastructure. The commercial LEO Destinations program, the one designed to replace the ISS, saw a crucial financial milestone this week. Starlab Space LLC closed a major strategic credit facility.
This financing deal, involving the U.S., European, and Japanese venture, is a major signal.
A signal to who?
To the market. It suggests that traditional financial institutions are beginning to view commercial space stations not as speculative venture projects, but as viable, bankable infrastructure assets.
That's a critical inflection point,
A
right?
huge psychological and financial one. The industry is moving past just relying on seed money and VC funding, and is starting to attract the long-term capital needed for these multi-decade projects.
And Starlab is also making a key architectural choice that's different from its competitors.
Correct. Competitors are focusing on inflatable habitats, but Starlab is using the Airbus Alupique concept, which is a rigid metallic module, an 8-meter diameter one.
Why go with metal over inflatable?
It's a deliberate choice. They're betting on the proven longevity and enhanced micrometeoroid protection that metallic hulls provide for long-term operations in LEO. While inflatable modules offer more volume, a rigid structure is often seen as a lower-risk option for a sustained commercial presence.
Meanwhile, China is enhancing the logistics for its Tiangong space station, moving from simple transport to enhanced capabilities with their new Qingzhou cargo spacecraft. What's the key innovation there?
Qingzhou is designed as a highly efficient, low-cost logistics vehicle. But the key innovation is the inclusion of a proprietary space refrigerator.
A space refrigerator.
A cold chain system, yeah, offering 300 liters of precise temperature-controlled volume.
Why is a refrigerator such a major focus for a nation building a permanent station?
It addresses two critical bottlenecks for long-duration human spaceflight. First, it allows for the transport of fresh food to boost crew morale and health. That's a huge quality-of-life factor.
And the second?
More critically, it provides a reliable way to transport highly sensitive biological and medical samples, tissue cultures, DNA experiments back to Earth without degradation. This closed-loop cold chain is essential for maximizing the scientific return.
And looking ahead to a permanent industrial presence on the moon, securing the energy needed for that requires massive power. We saw Russia and China solidify their plans for a lunar nuclear power plant.
The agreement centers on a plan to build a nuclear fission power plant on the moon by 2036. It's intended to provide continuous high-density energy for the Russian-Chinese International Lunar Research Station.
This is a crucial strategic step.
It is. It corroborates the universal understanding among all space powers that sustained long-term lunar operations, especially things like in-situ resource utilization, or ISRU, will require fission power.
Solar just won't cut it.
Solar power is simply impractical for getting through the long 2-week lunar nights and for the high-power demands of manufacturing. Nuclear is the only viable path forward for a permanent industrial lunar presence.
Finally, back to the immediate future of the U.S. lunar program. NASA completed a full wet dress rehearsal for the Artemis II crewed mission.
This was a major operational milestone. The 4 crew members boarded the Orion spacecraft and practiced the entire final countdown, fully fueling the rocket, simulating everything up until minutes before ignition.
Did it go smoothly?
The research team noted some minor technical delays related to the thermal barrier around the crew hatch that needed some attention. But the completion of this full high-fidelity rehearsal is the last major operational hurdle before the crewed flight to the moon.
So it puts the mission firmly on track for its launch timeline.
It does. So if you step back, the week of December 17th through the 24th, 2025, it really demonstrated a clear, almost painful divergence in the global space economy. The commercial West, driven by massive defense spending, the unstoppable cadence of SpaceX, the successful financing of next-gen infrastructure like Starlab, is accelerating the industrial scale of space and cementing its economic advantage.
While others are struggling to keep up.
Meanwhile, state-level competitors, specifically China and Japan, are struggling with the immense inherent difficulty of these sophisticated technologies like precise reusability. And that costs them billions in delayed capability.
And on the scientific front, our understanding of the outer solar system just changed dramatically.
The search for life is getting harder. It's pivoting away from the romantic notion of a vast global ocean on Titan to the more constrained, messier reality of localized, isolated cryoaquifers.
It forces astrobiology to fundamentally rethink how energy gradients, not just the presence of water, are what drive habitability. We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the Titan slush hypothesis, the implications of the $3.5 billion defense contracts, or the sobering reality of that Shenzhou rescue mission.
We've established that the SDA contract effectively extends the Aegis missile combat system into orbit. It's creating an undeniable fire control sensor layer. Space is now, without a doubt, a highly contested warfighting domain, and this infrastructure is absolutely critical.
So if this orbital infrastructure is now critical national infrastructure, here is the final provocative thought for you to mull over as you look up at the night sky. What is the next great technological leap necessary beyond propulsion and sensing, beyond just launching cheaply to proactively and sustainably protect this newly critical orbital infrastructure from sophisticated countermeasures? That's the real challenge that's going to define the space race of the next decade. Thank you for joining us for this analysis on Tomorrow Unveiled. We promise another look at the future, delivered today very soon.